Okay, so let me start by reminding some of the theorems, useful statements that we had from last week. So one of them was, what we had was for any mixed, so let me write it in this form. For any mixed strategy profile, let me use J. Okay. For any mixed strategy profile, for any agent, I and N, mu I was a best response of agent I to the mixed strategy profile. Again, I'm abusing language here. This is the mixed strategy profile consisting of the mixed strategies of all the agents except agent I, if and only if the support of mu I was a subset of the best responses of agent I to the mixed strategy profile mu minus I. Okay? So that was a useful theorem. By the way, remember the support consists of, again, in quotations, it consists of pure strategies of the player. That is, mixed strategies which pure strategy SI is played with probability 1. Okay? And one of the strengths of this theorem is that it's an if and only if statement, this proposition. So the other statement that we made use, and which is useful, that we will, which maybe you should make use of in the homework, is the following. A strategy profile, again, let me write it the long way, mu J, is a Nash equilibrium of the mixed extension game. Again, whenever I'm talking about mixed extension game, we're assuming that the underlying game is a finite game. If and only if the following two statements holds. One, for any agent I in N, the following statements holds. For any SI prime in the support of mu I, we have the expected utility of agent I from playing SI when the opponent plays according to the mixed strategy profile mu minus I is the same as the expected payoff agent I gets by playing SI prime, again, given that his opponents are playing according to the mixed strategy profile mu minus I. This and this for any SI in the support of mu I, and for any SI prime which is not in the support of mu I, we have the expected payoff of agent I from playing SI, from playing the strategy that is in the support, given that his opponent plays according to the mixed strategy profile mu minus I, is at least as much as the expected payoff that he would get by playing SI prime, given that his opponents play according to mu minus I. Okay? So those were the two statements that we had. So to find Nash equilibrium, all we have to do is find mixed strategies which satisfies these conditions, which mathematically is not hard. There are a bunch of equalities and inequalities, all linear. Okay? So all you have to do is solve them. The problem is, usually there is too many of them. Okay? So it would be nice if we could eliminate some cases, some situations. Okay? Again, to decide on what we can eliminate, one of the things that comes to mind is using this fact, okay? So if a pure strategy is never a best response, okay, then any mixed strategy which gives a positive weight to that pure strategy cannot be a best response, and hence cannot be a part of a Nash equilibrium, right? Okay. So if a pure strategy is never a best response, this condition never holds. So any mixed strategy which gives a positive weight to such pure strategies can never be a best response, and hence it cannot be a part of a Nash equilibrium. So if there are any such strategies, then we can automatically deduce that the player will never play them with a positive probability, okay? So that's one thing that we will use to eliminate it. So let me write that formally. A strategy SI prime of player I is never a best response of player I, of agent I, in the mixed extension game. In the mixed extension game, if and only if. So formally, what is that? Formally, how would I define this? Well, no matter which mixed strategy profile the other agent plays, I'll write J different than I. So whenever you see this, you should understand that J is an element of I and different than I. Okay, so I'll use this shorthand rather than this long statement. Okay. So for any mixed strategy profile of the opponents, there exists a mixed strategy of player I such that the expected payoff agent I gets by playing the mixed strategy mu I, given that his opponents are playing according to mu minus I, is greater than the expected payoff that he would get by playing SI, given that his opponents are playing according to mu minus I. Okay? That's what we understand from never best response. Okay? So far, so good? So, okay. So, if for a strategy of player I satisfies this condition, we automatically know that he will not play it with a positive probability just from this fact. Okay? But then checking this is not much fun. You have to check this for every mixed strategy profile of the opponents. And for every mixed strategy profile of the opponents, you have to show that he has a mixed strategy. So this doesn't look something easy to check. One might say, I'll rather check this than checking this. Okay? Fortunately, we do not have to check for every mixed strategy profile of the opponents. All we have to do is proposition. All we have to do is check it against pure strategy profiles of the opponents. So, yeah. So I'll write it shortly. SI, in capital SI, is never a best response of player I in the game gamma m, in the mixed extension game. Okay. If and only if there exists a strategy profile of agent I, there exists a mixed strategy of agent I such that no matter which pure strategy profiles of the other agents, no matter which pure strategy profile the other agents play, the expected payoff that agent I gets from playing mu I, given that his opponent plays the pure strategy profile S minus I, is greater than the expected payoff that he would get by playing SI, given that his opponents are playing according to S minus I. Okay? This simplifies the task quite a bit. Rather than checking for all mixed strategy profiles, we just check for pure strategy profiles. Okay? This is a finite set, that's an infinite set. Okay. Yep?
Does this come from the fact that mu minus I is a convex combination of S minus I?
Okay, I'm glad that you asked. So it looks like this trivia follows from the definition, right? So what you're probably doing is, okay, taking the convex combination of both sides, taking the convex combination of this side over S minus I, the same thing over S, so multiplying both sides by mu minus, so multiplying both sides by J different than I, mu J, Sj, okay? Adding them up, right? Then you replace this for all S minus I with mu minus I, okay? So this part implies that part, but then there is a problem. Here, the universal quantifier for all mu minus I is in the inside. Here it's outside. And we cannot interchange an universal and existential quantifiers. Okay? So this directly does not imply this by just taking convex combination. We need more than that. Okay? Well, depending on how we feel and how things go, maybe I'll give you a proof of this toward the end. Okay? Greater. Okay, because if it's equal, it might be a best response. Okay, so to make sure that it's not a best response, we have greater. Okay, so far so good. So, example for this. Let's take a simple game. Left, right, top, middle, bottom. I'll just write the payoffs for player 1. That's a standard game. Okay. Take this game. Okay. So let's call, well, I'll write that. So U1 of, okay, mu1 L. I'm checking against pure strategy of player 2. Okay. What is that equal to? That's mu1 of T times 3 plus mu1 of M times 0 plus mu1 of B times 1. Okay. Which is equal to 3 mu1 of M plus mu1 of B. Okay. Did I make a? Oh, yes, T. I'm sorry. Yeah. top. Okay? And U1 of mu1 m, I'll write that simply. What am I doing? Not m. R is 0 times mu1 of t times 3 times mu1 of m plus 1 times mu1 of b. Okay? So that's this side. Well, I claim that B is never a best response. Okay? I claim that B is never a best response. Okay? So to show that, what do I have to do? I have to show that player one has a mixed strategy, okay, for which this number is bigger than 1. So that's, I'm going to write here, U1 of B L, U1 of B R. So I'm just checking against pure strategy profiles of the opponents. Okay? So if I say that B is never a best response, it means that I can find a mixed strategy profile for which this condition holds. Okay? So can you give me such a mixed strategy profile? For example, right? So play T with probability 1 over 2, M with probability 1 over 2, B with probability 0. So that's 3 times 1 over 2 plus 0. That's 3 over 2. That's bigger than 1. And again, that's 3 times 1 over 2 plus 0. That's 3 over 2. Again, that's bigger than 1, which is equal to U1 of BR. So we know that B is never a best response. So no Nash equilibrium will consist of a mixed strategy of player 1 at which B is played with a positive probability. Okay? Which simplifies my task. So when I'm using this theorem, or when I'm using graphs, whatever, but essentially for this theorem, when I'm using this theorem, I do not have to consider the strategy of player 1. I know that player 1, at any Nash equilibrium, player 1 will play B with probability 0. Okay, because of this case. So far, so good? So far, so good? So that's a way to simplify the task of finding mixed Nash equilibria of mixed extension games, or as it's said in literature, mixed strategy Nash solutions or equilibrium. Okay? So far, so good? So let me change this game slightly. Let's make this a 2. Okay? Yep. Uh-huh. Okay, so in the pure strategy game, B is not a best response. So it was not a best response in this game, and it is not a best response in this game. So let's see what happens in the mixed extension game. Okay, so in the mixed extension game, what we will have is here we'll have a 2, here we'll have a 2, and actually let me erase this part. I'll just write this. 3 mu1 of T plus 2 mu1 of B. So here we have 2, which is U1 of BL. Here we have 2, which is equal to U1 of BR. Okay. So in the mixed extension game, B is never a best response if there exists a strategy of agent 1, a mixed strategy of agent 1, for which these two inequalities hold. But if these two inequalities hold, what happens? Let me erase this part. If these two inequalities hold, add them side by side, what do you get? 3 mu1t plus 3 mu1m plus 4 mu1b, which will be equal to 3 times 1, because mu1t plus mu1m plus mu1b will give you 1, okay? Plus mu1b, we had an extra b from here because there's 4 mu1b's, is greater than 4. So if B is never a best response, then these two inequalities hold. If these two inequalities hold, then this inequality holds. But can this inequality hold? Right? Mu1b can be at most 1. So this number can be at most 4. But we're saying that it's bigger than 4. So a contradiction. So what led to the contradiction? The assumption that B is never a best response to led to the contradiction. Which means that because the statement is an if and only if statement, it means that B is a best response, even though it's never a best response in the pure strategy game. It's a best response to some strategy profile of the opponents in the mixed extension game. For example, which strategy profiles? Can you give me a mixed strategy of player 2 for which B is a best response? Sorry? Alpha?
Just
1 over 2, 1 over 2, right? Half, half, that's what you were saying. 1 over 2, 1 over 2. So if player 1 chooses the strategy, play L with 1 over 2 probability, play R with 1 over 2 probability, then B is a best response to this mixed strategy of player 2. Okay? So that's an answer to your question. Your friend's question was, does being never a best response in the pure strategy game imply that it's going to be a never best response strategy in the mixed extension game? Not necessarily. Okay? So far, so good? Okay. So, before you jump the gun and start using this theorem, it might be a good idea to check if there are strategies which are never a best response. And then, in quotation, eliminate them. Eliminate in the sense that we know that at any Nash equilibria, those strategies will be played with probability 0. Okay? So far? So good? Any questions? Okay. So let's see, what was the next intention? Okay. So let's see. I keep changing my mind about on how much detail to go into. And just I was talking, I still changed my mind. So what else can we say about the set of Nash equilibria in the mixed extension game? Again, first of all, we know that every mixed extension game of finite games does have a Nash equilibria. Okay, so we know that it's non-empty. And then when it's non-empty, you can ask about its structure. So you can talk about algebraic structure, topological structure. So you can ask, is it a convex set? The set of Nash equilibria of mixed extension games? Actually, we already know the answer for that, right? For example, in the Battle of Sexes game, we had 3 mixed strategy Nash equilibria. Okay, but if it was a convex set, any convex combination of mixed strategy Nash equilibria would be a mixed strategy Nash equilibria, okay? Which means that there would be infinitely many of them. There's only 3, so it can't be. Again, when I say convex combination, what do I mean? When you have a finite set, okay, a mixed strategy, we can think about it as a function from Si to R, such that summation mu I Si, R plus, let me say, is equal to 1 over Si in capital Si. Or you can think about it as Si1 mu I Si2 mu I Si k, where k is the cardinality of Si. Okay? So you can think about it as a vector, as a list, where the first component tells at what probability the strategy Si1 is played with. The second component tells us with what probability Si2 is played with, and so on. Actually, that's the notation that we used when we found the mixed strategy Nash equilibrium of the Battle of Sexes game, right? We said, what was it? 2 over 3, 1 over 3, 1 over 3, 2 over 3. That was a strategy of player 1, a mixed strategy of player 1. That was a strategy of mixed strategy of player 2. We used it as a tuple. So mixed strategies you can think about as vectors. Hence, you can think about it as elements in a Euclidean vector space. So when I talk about convex combination, that's what I mean, convex combination in the usual sense of Euclidean vector spaces. And we can talk about topological properties. Is it closed? Is it open? And so on. Okay. Again, when I talk about openness, closedness, I'm using this notion. So closed in the sense that it's an element of a Euclidean metric space. So what can you say about the set of Nash equilibria? These are side remarks, not maybe more advanced level things. But if you remember, when we proved the Nash existence theorem, what did we use? We used Kakutani's fixed point theorem. But in the Kakutani's fixed point theorem, we defined a function B, which was from Si to, not Si, S, the Cartesian product of Si's, to S. Okay? And actually, we proved that this had a closed graph, because that's what we needed in order to use Kakutani's fixed point theorem. Using the fact that the best response correspondence has a closed graph, you can show that the set of Nash equilibria of any mixed extension game is a closed set. That is, it includes its boundaries. Okay? Side remarks. Any questions? Okay? That's a simple exercise. Just for the fun of it, I would recommend that you try it. If you write a proof and like to share it with me, I'd be happy to take a look at it. Okay? Any questions? Okay. So, 2 options. Would you like to work on another example for mixed strategy profiles, or the next topic I'm going to talk about is correlated equilibrium or correlated solution concept? How many of you have heard about correlated solution concept? Did you do it in microeconomic theory too? No? No correlated equilibrium, correlated solution concept? Okay. One more example? Okay, let's give it a try. Actually, I was thinking about an example from the book. I usually don't like to do direct examples from the book because it's available in the book, but this time I will do it because, it's a game represented in parametric form, so I would like you to get a taste of that. So this is an example from Osborne's book, which is again on reserve. Page, so you don't have to write it. I'm mostly going to be doing his example. Page 123, that's example 4.6. Expert diagnosis. The game is expert diagnosis. So the story is you have a car, you have a computer, it's having problems, it broke down. You take it to a repair shop. You can't repair it yourself, it requires some expertise. Okay? Well, let's say computer or car. The problem could be a minor problem, or it could be a major problem. Okay? The probability that it's a minor problem, let me see what, well, I'll use the same notation that Osborne used, and actually I don't like the notation, but I'll use it so that you can easily follow it. So the probability that the problem is a major problem is equal to R. A number strictly bigger than 1 and strictly bigger than 0, strictly less than 1. Okay? So essentially what this means is that, among all the people who own the same car, the same computer that you do own, those who had problems, okay, 100 times R% of them had a major problem. 100 times 1 minus R% of them had a minor problem. That's how we come up with the probabilities. You're a random person in that society, so that's what it is. Okay? So you take it to a repair shop. You take it to an expert. Well, the expert could tell you the problem is a minor problem and charge you a fee for a minor problem repair, or could tell you that the problem is a major problem and charge you a fee accordingly. Okay? So the fee, Osborne uses the letter E to denote the fee, the cost to the owner of a major repair, and he uses I, the cost of a minor repair. Okay? So, well, if he says the problem is a major problem and charges you, and you accept the offer and charges you, and actually the problem was in reality a major problem, then the profit of the firm is, the expert is, pi. So actually this is the only symbol that I like here, because pi, the first letter for profit, I have no idea what E has to do with major. I has to do, well, I could be the I of minor, but anyhow. You see, the symbols that you pick should resemble what they stand for. Otherwise, with a whole bunch of symbols, you might get lost on, what is what. Okay, so when you're choosing your symbols, choose them carefully for your own sake and also for your reader's sake. Okay, so pi is the profit that the firm would get when the problem is a major problem and charged you a major problem cost, Or the problem is a minor problem and charge you a minor problem fee. Okay? So the profit is the same because a major problem requires more time, more tools, okay? All costly stuff. Even though the expert is charging you higher, his cost is also higher. The minor problem, it's easier to fix. It takes less time, less tools, okay? So the cost to the firm is less, but the revenue is also less. So in both cases, we assume that his profit is the same, okay? Of expert, or what does, yeah, he calls it expert. From charging major fee I don't want to write it twice. Major, minor repair fee for a major, minor repair fee. Okay. And we'll use pi prime. Well, Osborne uses pi prime to denote profit of the expert from charging a major repair fee for a minor repair. A minor repair requires less time, less tools, so the cost to the firm is less, but he charged a higher amount, so his profit is larger. So pi prime is bigger than pi. And they're both, we're assuming, are positive. Okay? So far, so good? Well, as a consumer, you can accept the offer and pay E or I, depending on what the expert charge you, or reject the offer and look for an outside option. Take it to another shop, work on it yourself. Okay? Well, if you take it to another place or take the outside option, then again, there are two associated costs. There are two associated costs. E prime, the cost to the consumer, to the owner, the cost of outside option when the problem is major, and I prime, the cost of the outside option when the problem is minor. Okay? We assume E prime is bigger than E. Well, when you take the outside option, you have to search for a new shop. You have to work on yourself. You're not an expert. It's going to be more time consuming, and time is valuable. You have to go around, find another shop, search, and all that stuff. Okay? We'll assume that E is bigger than I prime, and that's bigger than I for the same reason here. Okay? You have to search, even if the problem is minor, you have to search for another store, for another repair shop, and so on. Okay? So, that's the game. So, when you take your computer, your car, to the repair shop, the expert has two options. He can be honest and say, you know, it requires a minor repair when actually it does require a minor repair, or a major repair when it actually requires a major repair, or could be dishonest. Of course, the dishonesty in this case could only be when a minor problem, it says that a minor problem requires a major repair. Okay? So, the expert has two strategies. Be honest or be dishonest. The consumer has, again, two strategies, accept the offer made by the expert. He says, he says, pay E or pay I, accept, or don't accept, reject offer. Rather than D, let me use R. Okay? So that's a simple 2x2 game. So let's fill in the payoffs. Okay? So the interesting thing about this game is, once we fill it out, it's going to be a 2x2 game. And then it's easy to find the mixed strategy Nash equilibriums, which one of the three methods that we already studied, using the two methods that relies on graphs and the third method which relies on the theorem which I just erased. Okay? So, modeling. We have to write payoffs here. There's some randomness involved. I happen to delete that. Yeah. Here. R, with some probability, the computer has a minor problem. With some probability, it has a major problem. So, what do we have? Let's start with the easy. The expert is honest, and then the consumer accepts the offer. What is the expected payoff of the expert? It's going to be pi, right? Because with our probability, the problem is going to be major. Well, his profit in that case is going to be pi. With 1 minus r probability, the problem is going to be minor. Again, his profit is going to be pi. So that was easy. Okay. What about the consumer? Minus? So, come again? Okay, because they're all cost, we have the minus. Okay, so the consumer prefers a lower cost to a higher cost. That's why your friend put the minus, I guess. Minus RE. So with R probability, your computer will have a major problem. Because the expert is honest, he's going to charge E liras on it. And minus, actually, let me do it like this. Minus 1 minus R. So with probability 1 minus R, the problem will be a minor problem. And being an honest expert, he's going to charge I units from it. So that's the expected payoff of the players when the expert is honest and the consumer always accepts the offer. Okay, so let's look at that cell and then we'll take a break. Mm-hmm. It will be 0 for the. So the expert is not honest, which means that he's not honest means what? Well, he will always say it's a major problem, so he will always charge E. Okay? So, but then what will happen? With our probability, it will truly be a major problem, and his profit is going to be R times pi, right? The profit from fixing a major problem and charging a major problem cost was pi, which is the same as fixing a minor problem and charging a minor problem fee. Okay? But with 1 minus r probability, the problem will be a minor problem, but it's still charging a major problem fee. Okay? So with probability 1 minus r, his profit is going to be pi prime. Because if he charges a major problem fee for a minor problem, his profit is no longer pi, but is a larger profit, which is pi prime. Okay? So far, so good? So, what is the consumer's payoff? Minus E. So it says, no matter what the problem is, the expert says, you have to pay E. Okay? Whether it's a major problem or a minor problem. So that's E. Okay? So far, so good? Minus, yes, exactly. Thank you. Again, that's a cost, so we put the minus. Any questions so far? Any questions so far? Yes, ma'am.
About the payoff of the expert. I thought
Which cell?
in case it is dishonest.
This case?
Yes. I thought that it should be pipeline instead of this.
Well, so with our probability, problem is major. Problem. Well, what did he charge? He was dishonest and said, you have to pay E. He said, it requires a major fix, so he charged E. In that case, what was his profit? Profit of an expert from charging a major repair fee for a major repair problem. Okay? So with our probability, the problem was major. Okay? And he charged a major problem fee, so his payoff is pi.
But is he dishonest?
Sorry?
Dishonest in this case?
Well, so, well, the thing is, so when we said dishonest, you know, and let me say quotations. So if I'm dishonest, would I charge a minor repair fee for a major problem?
It's not rational, but what I'm trying to say is that if you think about it that way.
So when we say dishonest, actually what we mean is, so for a major problem, what I would expect from the expert is to do is always charge a major problem fee. But for a minor problem, the expert could tell the truth and charge a minor problem fee, or be dishonest and charge a major problem fee. So the dishonest part is only when the problem is a minor problem. Okay, so dishonesty doesn't mean that he always tells the opposite. He tells in a way to cheat you when he can. Okay? Let's take a break. I'm sorry, I went over time. And then after the break, we'll continue with your question. Did everybody sign the attendance sheet? May I have the attendance sheet, please?